Hi, it's Mrs. V here. Today we are going to be talking about how to do calculations using ice tables. Not really that kind of ice table. Let's get the whiteboard on and get started. So ice tables. Ice in ice tables stands for initial, change, equilibrium. And ice tables are useful for questions where we're not given the equilibrium concentrations of substances and we have to work them out using stoichiometry. So therefore, working out equilibrium concentrations using stoichiometry. So stoichiometry, remember, is your moles. So last video, we had lots of questions where we had to work out Kc, the equilibrium constant, but we were always given the concentration of substances at equilibrium. If we have a look at our question this time, 0.8 moles of HCl, 0.4 moles of oxygen, and 0.1 moles of chlorine are mixed in a 10-litre vessel and allowed to allowed to react at 220 degrees according to that equation. So we have our equation there for HCl plus O2 in equilibrium with 2H2O and 2Cl2. We know at equilibrium there is 0.3 of a mole of chlorine present. Calculate the value of the equilibrium constant. Now that is a lot of information all in one question. So we use the ice table to organize our information. So always start your ice table with the equation for the reaction. That's important because that is where we get our mole ratio from. So we always start with our equation. Luckily, the equation here is given to us. So we can see here that our mole ratio is 4 is to 1 is to 2 is to 2. So when the reaction's occurring, everything's occurring in accordance with that mole ratio. What we're going to do as our second step is we're going to write in our initial numbers of moles. Sometimes it's moles in the question, sometimes it's concentration. This one's moles. So you can see we're given 0.8 of a mole of HCl. So we're going to write 0.8 in the table for HCl. We don't need to multiply it by 4 or anything like that. The only thing that obeys the mole ratio is the change row. So the mole ratio is important only for the row of the table that has the changes. So then we're going to put our 0.4 moles of oxygen. We didn't have water mentioned at all in the question for the stuff that was put into the reaction vessel, so we can assume that water is 0. And we put in 0.1 of a mole of chlorine. So once we have our initial concentrations, we look for what final concentrations we're given, our equilibrium concentrations. And we're told at equilibrium, there is 0.3 of a mole of chlorine present. So we're going to write 0.3 in the table for our equilibrium concentration of chlorine. Now what we need to do is start working out what has changed. We don't know the equilibrium concentrations of the first 3. So all we know about is chlorine. And we can see that through the reaction, chlorine has gone up by 0.2 of a mole. It's gone from 0.1 to 0.3. So looking at our mole ratio, if we look at water, water has a mole ratio 2 is to 2, which is 1 is to 1. So if chlorine increases by 0.2, water must also increase by 0.2. Oxygen, the mole ratio between oxygen and chlorine is 1 is to 2. So if chlorine's increasing by 0.2, Oxygen, careful, is on the other side of the equation. Remember, here's our reaction, our equilibrium sign here. So if chlorine's going up, oxygen's going down. So oxygen will go down by 0.1. And HCl, mole ratio is between HCl and chlorine is 4:2 or 2:1. So you'll get twice as much change in the HCl as you will in the chlorine, which is 0.4. And you will have that going down because it's on the other side of the equation. Now that we know how everything has changed, we can work out everything's number of moles at equilibrium. So water started at 0 and ended up increasing by 0.2. So at equilibrium, that will be 0.2. Oxygen started at 0.4 and went down by 0.1. So that will be down to 0.3 now. HCl started at 0.8 and went down by 0.4. So that is now 0.4. Now we know the number of moles of everything at equilibrium. We have to be careful. This is one of the traps for young players. You do not substitute moles into the KC expression. You substitute concentrations. So you must work out your concentrations. So looking back at the question, you'll see that the reaction vessel was 10 litres. And we know that concentration is moles over volume, which means we're going to need to divide each of those moles by 10. So this is our concentrations are going to be 0.04, 0.03, 0.02, and 0.03. That is probably one of the more common mistakes that people make in this type of problem. So once we've got all of those, it now becomes just a normal old equilibrium constant question. So write the expression for KC. Products over reactants. So concentration of, maybe we'll start with H2O squared, concentration of Cl2 squared. And all of that's over concentration of HCl to the 4th, concentration of O2. Now we can substitute our equilibrium concentrations into that. So our water is 0.02, and that's squared, times by our chlorine is 0.03, and that's squared. Our HCl is 0.04, and that's to the 4th, and our oxygen is 0.03. So we put that into our calculator and run it through, and we come out with 4.65. So really, we're at one significant figure here, so that rounds to 5. Let's have a look at another example. I want you to have a go at this one. So I want you to pause the video and try this example here. Okay, we are back. The first thing we put in our table is our equation because we want our mole ratio. So we've got PCl5, and that's in equilibrium with PCl3 and chlorine. My favourite mole ratio, 1 to 1 to 1. Our initial numbers of moles, we were told that 3.0 moles of PCl5 was placed in that vessel. And that was all. It was an evacuated vessel. That means it was empty. So PCl5 was the only thing we put in there. So at the beginning, there was no PCl3 and no Cl2. What do we know? At equilibrium, 1.0 moles of PCl5 remains. So we put that in the equilibrium row. Now we can work through the changes. Remember, changes have to obey our mole ratio of 1 to 1. So what happened to PCl5? It went down by 2. Now that means PCl3 will also change by 2, but it's on the other side of the equation, so it's going to increase by 2. It could hardly go down, there was none of it to start with. Chlorine also is going to go up by 2. And that means our concentrations, or sorry, our moles, not our concentrations. At equilibrium, our moles will be 2 and 2. We now have to remember the concentrations. So looking back at the question, it was a 1.0 litre vessel. So that makes our situation nice and easy, because that means that if we're doing concentration as moles over volume, we're just dividing by 1. So our concentrations are 1.0, 2.0 and 2.0. Now, subbing into our expression for Kc, products over reactants, PCl3, concentration Cl2, over concentration PCl5. Sub in our concentrations, 2.0 times by 2.0 over 1.0, and you can see that Kc in this case is 4.0. Okay, that is how you use ice tables, and I will see you in the next video.